Hello everyone, today I'll be presenting Exemplar-Free Continual Transformer with Convolutions. Inspired from how human beings learn, continual learning or CL for short refers to a learning paradigm where a model can learn a new task without forgetting the previous task's knowledge. The necessity for research in this field comes from the fact that deep neural networks suffer from catastrophic forgetting. While this challenge of catastrophic forgetting can be tackled by retraining the model from scratch or training a separate model altogether, these solutions incur a lot of resource in terms of both time and compute. While there have been significant interest in CL, most CL approaches in computer vision have focused on convolutional architectures. There have been a few recent works on CL using transformers. LVT or lifelong vision transformers is one such approach which uses an inter-task attention mechanism that absorbs the previous task information and slows down the information drift between new and current tasks. Another approach called DITOX learns new tasks through expansion of new tokens known as task tokens. MEET uses learnable masks to help isolate previous task parameters that are required for current tasks. However, these methods have some limitations. LVT and DITOX requires to store few representative data samples or exemplars from previous tasks and use them when training for the new task. Hence, this cannot be applied for cases where data storage is not allowed. MEET requires task ID to be present during inference for the identification of task-specific marks. Therefore, this cannot be applied for cases where task ID is not available during inference. Tackling these challenges, we propose ContraCon, an exemplar-free continual learning approach based on transformers that does not require task ID during inference. Using convolutional task adaptation mechanism and a learnable skip getting to learn a new task, we are able to do so with very little memory overhead. We train the entire transformer consisting of n transformer layers on the first task. Each transformer encoder layer consists of a multi-head self-attention layer followed by a feed-forward layer. For learning subsequent tasks, we take the key, query, and value weights of the transformer encoder layer trained on the first task and convert them to current task weights using convolutional operations over them. Therefore, for each new task, we only need to learn a few convolution kernels. We also apply learnable skip getting for an effective trade-off between previous and current knowledge. Our inference phase consists of two parts. The first part involves task ID prediction and the second part involves class prediction. In task ID prediction, we pass multiple augmentations of the input image through various task-specific parameters and compare their average entropy. The parameters corresponding to the lowest entropy are considered. In the class prediction part, we pass the input through this version of the model to get the class prediction. We performed an extensive evaluation of our approach on various datasets and tasks formed out of them. Here are their statistics. We formed t tasks out of these datasets by dividing the classes in the dataset equally among all the tasks. For each experiment, we report the following. Accuracy averaged over all the tasks after the model has been trained on the final task. We report this for two setups. One, with task ID provided during inference, also known as the task incremental learning or the TIL setup. Another, where task ID is not provided during inference, known as the CIL or class incremental learning setup. We also report the number of trainable parameters required for the backbone architecture as well as the number of trainable parameters required per task in brackets. Here are the results on CIFAR-100 dataset. As you can see, even with 500 exemplars, the best competing approach, which is DITOX, can outperform ContraCon only in the 10 task setup. Here is a plot showing the parameter and accuracy bars of various approaches on the 10 task setup of CIFAR-100 dataset. ContraCon achieves the highest accuracy with the lowest number of trainable parameters. To highlight the importance of augmentation, we calculated the classification accuracy on the 10 task CIL setup over various datasets. As you can see, there is a performance drop without augmentation, highlighting the need for augmentation-based task ID prediction. So in conclusion, we proposed ContraCon, which is a novel CL approach using convolution over MHSA weights of the transformer for adaptation to new tasks. We adopted an image augmentation and entropy-based task ID prediction method, thereby removing the need for task IDs during inference. Through extensive experimentation and ablation of our proposed approach, we validated the superior performance of ContraCon compared to competing approaches.